Every serious piece of network gear still carries a connector that predates the internet. It is slow, it is fussy, and when everything else has failed, it is the only thing that still answers. Your laptop almost certainly does not have the port anymore, so you carry a small USB serial adapter, which recreates the old electrical world on one end of a modern machine. From the adapter runs the serial line itself. In the simplest form, it is 3 conductors, 1 wire transmitting, 1 wire receiving, and a shared ground reference between the 2 devices. Which wire is which depends on what kind of device you are. That distinction, terminal versus modem, is why the null-modem cable exists and why the wrong cable produces silence instead of a warning. At the far end is the console port, usually a small socket on the back of a switch, a router, or an industrial controller. It is the machine's mouth of last resort. Nothing about this link is discovered. Speed, data bits, parity, and stop bits are all set by hand identically on both ends. 9600 A101 is a convention, not a handshake. Behind the port sits the device you are trying to rescue. A switch that will not boot, a server with a broken configuration, a controller with no network at all, and no other way inside. And the modern twist. Most serial consoles are now reached through a networked console server sitting in the rack, so the oldest link in the building is delivered to you over the newest one. Take one, the switch is dead and unreachable. You plug the USB adapter into your laptop and the operating system presents it as a plain serial device. No network is involved anywhere in this picture. From the adapter, the serial line carries bits the crudest way imaginable. One after another, down a single wire with no packets, no addresses, and no headers wrapped around them at all. But first, the wiring has to be right. 2 devices of the same type would both shout on the same conductor, so a null-modem cable simply swaps transmit and receive between the 2 ends. Get that wrong and nothing happens. No error, no light, no complaint from either side, just a blank screen because there is no layer here clever enough to notice the mistake and report it. With the right cable, you push the plug into the console port. Nothing negotiates. There is no link state to come up, no address to obtain, and no driver on the far side to load. Now you set the parameters yourself, and so does the device, and they had better agree. Speed in baud, how many data bits, whether a parity bit is added, and how many stop bits close each character. 9600 baud, 8 data bits, no parity, 1 stop bit. That is the famous default. It was never discovered by the link. It is simply the setting almost everyone agreed to use. Set a different speed on one side and you do not get an error. You get streams of nonsense characters because the receiver is sampling a perfectly good signal at completely the wrong moments. With the settings matched, text appears, firmware messages, a bootloader prompt, a kernel dumping its complaints. The console is printing long before there is an operating system, a network stack, or a login. That is the whole reason it refuses to die. It works when the configuration is corrupt, the network is gone, and the software has not started. It depends on nothing above the wire. The electrical design helps too. The voltage swings are large and deliberately inverted, so the signal shrugs off electrical noise and survives cable runs that would defeat a modern low-voltage bus completely. In a real rack, you rarely crawl behind the gear anymore. A console server holds dozens of serial lines and lets you reach any of them across the network from your desk. Which is the quiet irony of the whole thing. The link you use when the network has failed is now, most of the time, delivered to you over a completely separate network. Look closely at one character on the wire. The line sits idle, then drops for a start bit, the data bits follow, an optional parity bit checks them, and a stop bit returns the line to idle. Flow control comes in 2 flavors. Hardware flow control uses 2 extra wires to say stop and go. Software flow control sends special characters inside the data stream to do the same job. The classic failure follows immediately. One side asserts stop and never releases it, so the terminal simply freezes. Nothing is broken, nothing times out, the link is politely waiting forever for permission. So where does it still live? Switch and router consoles, factory controllers and sensors, laboratory and test instruments, medical and marine equipment till peripherals and every out-of-band management path worth having. So the whole picture: a laptop, an adapter, 3 wires, settings agreed by hand, and a port that prints before anything else exists. No addressing, no negotiation, no dependencies, and therefore nothing left to break. That's the whole trick. Next time you see a lonely socket on the back of a rack, remember it is not a leftover. It is the last thing that still talks when everything modern has given up. Follow how it all runs for more. See you next time.